So today we will understand about backpropagation in CNN. We learnt about backpropagation in multi-layered perceptron. Now it is very important to understand this in CNN as well. Most people actually skip this part, but it is very important to understand what is happening in details so you can actually understand the core of it. Okay, so before we start with backpropagation, let us understand forward pass in CNN. This is very simple. This is basic convolution. So you have an input here and you convolve it with a filter and then you move forward. Once you get the output, then you will convolve it again and then you will get another output, and so on. You will go on until you get the final required whatever you are searching for. It might be segmentation, it might be classification, or so on, right? So we have to understand about forward pass. So let us suppose these are our input values and this is the filter values. We are getting an output. So this is our output feature map, and let this be O11, O12, O21 and O22, right? So what we will be doing is we will be understanding this one more time once again. So what will happen is first we will place our filter at the left topmost corner to get the value of O11. So this will be equal to, our O11 will be equal to X11 into F11, this into this plus this into this. So X12 into F12 plus X21 into F21 and finally X22 into F22. So this is how we get our value O11. In the same way, what we can do is now we will shift our filter here. So we shifted our filter by a stride of 1 and then we will get the value of O12 in the same way. Okay, so O12 will be basically the same thing. You will go on again with X12 into F11. Now because this is here and this is here and so on, this will continue, and in the same way you will get the values of this, this, this and this, right? Okay. So here we have, this is a very good animation to show what is happening. Obviously you understand the thing, but it is very important to understand what values we are getting. So first we will put here and then we get the value this. Then we get this value for O12 and O21 and O22 finally, right? So we will be just shifting our filters like you can see here, and then we'll be multiplying the values. Here you start, you have here, and then you multiply, you get the values, you multiply, you get the values. Once after getting the values, you will add the values. So that is what basically it is happening, right? I think it is simple to understand. So this is basically forward propagation. So these values will now constitute one feature map that will look like this, right? Now this feature map can again be convolved and you can keep moving forward with it, or maybe you are done with all the convolutions and you can flatten it to a dense layer, and then you can again go on with whatever is required, whatever the task requires, right? It can be different things, but this is the basic thing of forward propagation. So you are moving forward. Now let us come to what is known as backpropagation. So here you have this O11 and we are just going to use O11 for now, and then I will explain everything else later on. You have O11 here, right? But now to basically find out what is happening, we will be doing the partial derivatives with respect to F11, F12, F21 and F22. So why are we doing it with respect to the filter values? So you need to understand, even when you were doing multi-layered perceptrons, right? What we were doing is, when we were differentiating loss, we were differentiating it with respect to the weights. So what this basically means is, whenever we have a loss, we will differentiate it with our trainable parameters, because our weights were trainable parameters in a multi-layered perceptron. But here in CNN, the idea is very different. So in CNN, what you happen is, you have to change the value of the filters. So you remember one filter we had was like this, +1, +2, plus 1, 0 0 0, then again minus 1, minus 2 and minus 1, right? So this was for edge detection. So you may require way more features than this, and you cannot remember the filter values obviously. So the best part for this is for the model to itself figure it out, and hence what we will be doing is we will be using filters for this. Now this filter we know, but others we do not know. To find those values, we will be updating the value of the filters. Hence, since the value of the filters need to be updated, so what will happen is we will differentiate the loss with respect to the filter values, right? So that is why we will be differentiating with respect to filters and not x or anything else. Okay, so we have O11, so you will be differentiating that with F11. So if you differentiate the whole thing, what will happen is the rest will go off to be 0, because we are doing partial derivatives. So for partial derivatives, everything else is constant. So now you will be differentiating this and you will get x11. In the same way, if you differentiate O11 with respect to F12, you will get x12, and so on, right? So in the same way, once you have done O11, you can do the same thing for O12, O21 and O22. But there is a catch here. So the catch is basically, if you look into this, for O11 you are requiring F11, but the same time for O12 also you are requiring F11, because we are using the same filter over and over again. So to actually find the differentiation with respect to filter value is going to be more difficult or different than this. So in that case, what we do is basically we differentiate all the values of O with respect to the same F1. Then we differentiate again all the values of O with respect to F12 this time. Then we differentiate all these with respect to F21 and then F22. So what that basically means is you will first differentiate O11 with respect to DF11. Then you will differentiate O12 now with respect to again DF11. Then you will differentiate O21 with respect to DF11, and finally O22 with respect to DF11. So what that basically means is you will be differentiating all these values for the same F11, and finally you will add the whole thing and you will get the final differentiation of O with respect to F11, right? And that is how you will update the value. Let us understand that in more details. So first you have differentiation of loss with respect to DF. Okay, now the first thing that you need to understand is you have to differentiate the loss with respect to the output first, and then you have to go into F. So what will happen is differentiation of loss with respect to O, and then that differentiation of O with respect to F. So this is basically breaking it down into chain rule. So you have now the differentiation of loss with respect to the output, and then the differentiation of output with respect to the filter value. So this is how it will happen. So now that we are clear on this, let us now understand the whole differentiation of loss with respect to the filter value. So in that case, what will happen is we will apply the chain rule first. It will happen differentiation of loss with respect to output, and then differentiation of output with respect to differentiation of the filter value. But like I said, we are having many outputs that use the same filter value. So in that case, what we will do is we will just add all these values up, right? So this is how we are getting the value of filter 1, and then differentiation for filter 2. Then again, if you are using maybe gradient descent or something like that, what you can do is for the next filter F11 new will be equal to F11 old minus eta times of differentiation of loss with respect to DF11. So now you basically understand what is happening. So we have loss, and we need to differentiate our loss with respect to our filter values, right? But there are a lot of problems that we have come across. The very first value is we cannot differentiate directly because we have our output kernel as well, or output feature map. So to solve that, what we have done is we have broken this down for the chain rule. So now we have differentiation of output with respect to differentiation of loss with respect to output, and that is multiplied by differentiation of output with respect to the filter value, right? Okay, so Now that is done, the next thing that we will do is we will understand this part. Since all the outputs will be using the F11 or the same values of the filter, so what we will do is we will basically differentiate all of these with the same F11. So you will have differentiation of O11 with respect to F11, differentiation of O12 with respect to F11, O21 with respect to F11, and so on, and in the same way for everything else, and then we will finally add the whole thing up. So this is how basically we get the differentiation values. So now if we remember, when we were differentiating O11 with F11, we were getting X11, and in the same way we were getting X12, X21 and X22, if you remember the whole thing. So what we can do is now we can substitute these values to the values here that we have. Okay, so what will happen now is we will have dl by df11 will be equal to dl by do11 into, now this was x11 plus dl by do12 into x12 and so on, right? So our values will come out to be something like this, right? But here if you look carefully, this is basically what? This is basically the convolution of, if you see, x11, x12, x21 and x22. So if you see the first part, let's suppose dl by df11, so this is basically the convolution of x11, x12, x21 and x22 with dl by do11, dl by do12, dl by do21 and dl by do22, right? If you will see the whole thing, this is basically in a convolution format itself. So what that means is we have this whole thing. So basically differentiation of loss with respect to F11 will be the convolution of the whole thing with a differentiation matrix. So this is basically what I was trying to say, and these again will be from the other values while moving forward. So when you will be back propagating, you will be getting these values on your own, and once you get these values, you will be convoluting it with all these x values. So the whole thing, the whole point of this was basically to find the values. We will just, for backward propagation itself, when we were forward propagating, we were convoluting. In backward propagation, again to update these values, we will still be doing convolution, but the matrices will keep changing. So this is basically the whole thing about back propagation in CNN. So in short, what you can write is differentiation of loss with respect to f will basically be a convolution of input of x, that was the input matrix, and this will be convolved with what? This will be convolved with a loss gradient matrix. So this loss gradient matrix is basically dl by do. So this is basically how we will be updating the values of the filters. Okay, so I know this is a lot, but in short what we are doing is, when we are forward propagating, we are convoluting this with filter values, convoluting the input with filter values, and then when we are back propagating, what we are doing is we are again convoluting to back propagate and update the values, but this time what we will be doing is we will be convoluting the input again, but with the loss matrix this time. So this is basically the whole thing. So now you will get the values that you need to update. Now just put this into the whole formula of gradient descent or whatever descent you are using, whatever optimizer. So basically now the new f will be equal to the new old f matrix minus eta times of dl by df, and this value you are getting from convoluting. So this is basically the whole thing. Even if you do not understand how the whole proof I made and showed, you can still understand that this is what is happening. and it is very important to understand the very basics of it, because then you can actually answer good questions for interviews obviously, but at the same time your concept will be very clear to solve more difficult problems. Okay, so that's it. Enjoy learning.